This is Chuck Knox. It is October 24th, 2022, and I am going to be presenting a talk October 27th of 2022 for the Michigan PTTC, the Michigan Geological Repository for Research and Education. It's also sponsored by the Michigan Geological Survey at Western Michigan University and the Michigan Oil and Gas Association. And this talk is going to be using lidar-derived flow accumulation models as an exploration tool in the southern reef trend of the Michigan Basin. It's part of a talk on data technology and practices, which is good. This is the lidar is a lot of newer technology and a lot of data, so this fits very well into the talk. Linda Harrison asked me probably June of 2022 if I would give a talk for this, and I said, what are my limitations? And she said that it has to be on the Michigan Basin, and I said, deal. So we've been working with the reef trend in Illinois and Indiana, and working with Knox erosional remnants in Indiana, and done some work in Morrow County, Ohio. And these flow accumulation signatures tend to track these reefs and erosional remnants quite well. So I wanted to see how they would track the southern reef trend in the Michigan Basin. And that's what this talk is going to be about. It's basically two parts. I wanted to go through methods of how we're isolating these flow accumulation signatures, and then the results of the survey. This talk is dedicated to Martin Eisenberg. We lost Martin September 9th, 2021. Martin was really the founder of the industry, and we miss you greatly, Martin. Thank you. Without Martin, none of this is possible. I also want to thank the EGLE and the Geo web face. It's this portal to download geologic data is a wonderful tool, and it's helped me tremendously on this this talk I put together here. What I want to do now is start what the LiDAR is, and it's an extremely accurate laser survey. Surveys can be very large, such as a statewide airborne surveys, or very small, such as a scan of a human tooth. And it's a very powerful tool. We can strip away vegetation and man-made structures to capture digital data of the bare Earth surface. And that digital data, in turn, can be used in the exploration of oil and natural gas. And it is a technology that is becoming increasingly important to many industries and many municipalities. But what LiDAR is not, it is not a standalone, at this time, remote sensing tool that can identify areas capable of producing oil and natural gas. What it is a way for us to pick locations to run reconnaissance 2D, and then the eventual run the 3D, and then with the 3D we can pick locations to drill. LiDAR works by a laser scanner. The large airborne surveys are flown either helicopter or plane. You can handheld scanners, backpacks, drone, cars. There's many ways you can carry the emitter. So you emit a laser pulse to the surface. That pulse is reflected back to a receiver, and the time is measured, the intensity, the angle is also measured, and a GPS coordinate is given to it. And so then we have an XYZ for each point, and so the result then is, with all of them together, is a cloud of points, and this point cloud data is what I work with, and that's where we get our flow accumulation models, is from that. I wanted to document just how I go through making a flow accumulation model. There's many steps to it, and each step is fraught with danger. There's a lot of work to it, and if you take the time and work through it, you too can run flow accumulation models. And if you give it a shot and have some trouble, and just give me a call and we'll work through this. Here is Calhoun County, east of Battle Creek, Michigan, and you can see the historic drainage as the glaciers were melting. These huge channels of the water were flowing underneath the glacier and creating just a very chaotic surface. And it is very tough to make any determination from this surface. And what the flow accumulation does, it takes slope angle and it takes elevation, and it creates a flow accumulation model from that. And then we can simplify this down to where we can start making decisions now. So with this simplified version of that surface, remember, this is a digital representation of where stream flow should be. Now we can start looking at this and looking for our flow accumulation signatures. Here's Ingham County. This is in the Lansing area. Again, you can see the historic stream flow, most likely under the glacier. It's a very chaotic surface and tough to make any determination from. Now, as we go to the flow accumulation model, you can see that the data has been reduced down to a simplified version and something that we can actually start making decisions with. There are two types of flow accumulation signatures that we find work well with the reef trends in Illinois and the erosional remnants in Indiana and Ohio. Number one is a radiating stream flow. We get flow accumulation emanates from a central point. And type 2 is a deflected stream flow. Flow accumulation is deflected in a circular pattern around a central point. Most signatures exhibit a combination of both radiating and deflected stream flow. Here is flow accumulation example 111. It shows a radiating stream flow. It shows stream flow radiating from a central point. We have oil wells in this one. We had a couple of dry holes in this one. On the southwest side, you have a deflected stream flow. And then you have radiating stream flow to the north, northeast, southeast, and southwest. Here is flow accumulation example number 149, and this has deflected stream flow. As you can see to the northwest, curving all the way around to the east, you have deflected stream flow around it. You have two streams that flow from the south to the north and then are deflected around this signature. And then on the northwest, the east, and the north, you have radiating stream flow. So these are two very good examples of what we're looking for in a signature. Now this is how I mark these things. I make a scan of the usually it's a county. I'll do a county wide, and I start at 1 to 24,000, and I will scan from the west to the east, and then I will drop down to the south, and then I go from the east to the west, and so I scan an entire county, and then I make shape files of these signatures, and so everything then has a number then, and I can then mark at this smaller scale, and then we look at it at the larger scale. So here's 1 to 24,000. So I go from west to east, down to the south a bit, and then from east to west, and I just make a pass over the entire county. And then when you're done with the county, this is what it looks like. So we have our flow accumulation model underneath, and then we have all our flow accumulation signatures. This is 1 to 150,000. And there's a rhythm to these things. If you look, 1, 2, and 3, and 4, and then they get larger to the east, and then you drop down, and then they get larger to the west, the numbers, and then you go back and forth. When I'm marking flow accumulation signatures, I will make two passes at it. The first pass is without any culture, without oil wells, without any oil fields, just purely flow accumulation. This builds from past experiences, so I use the data, the information I've learned on other projects, and then I mark these areas. What I also do then is I come back and I will put oil wells in, oil and gas wells and dry holes, and see where these, if there's accumulation of oil and gas wells, is there a signature and what that signature is. So that helps me kind of going forward in the future, that I can learn more about what's going on. And so here's an indication too of two signatures. Number 55 to the south and the west was from my first pass, and the 110 is from the second pass. And as you can see, if I were to be going from west to east, we'd have 55, and it should be like 56 or 57 right in the area. But since there's a big jump between the two, I know that 110 was a second pass. And I passed on this one because of that large tail that goes right through the middle of 110. But then when you put the oil wells in, you can see it's a pretty good structure there, and deserve to have a signature marked. Now let's get into the survey. I ran 4 counties: Calhoun, Eaton, Ingham, and Livingston. You can see where they're placed in the central part of the state. Zoom in a little bit: Calhoun, Eaton, Ingham, and Livingston. This is my digital elevation models, rasterized image of the surface. And then there I put in my flow accumulation signatures over the area. So as you can see, there's a bit of a rhythm to them. They seem to follow a trend right here, and we're finding that with most of these reef trends, that there is a rhythm to these things. And I'm not a huge student of reef architecture, but it's just got kind of a reefy look to me. Let's take away the digital elevation models, and now we're left with just the signatures in the 4 counties. And again, you can see the rhythm to it. We have areas of larger signatures, more densely packed signatures. And now what I want to do is the data from the GeoWeb face. Now these are Silurian oil wells I want to put in here, and that's all I've got is just Silurian oil wells, and I want to put those in. And as you can see, the Silurian oil wells are matching up nicely where we have a high density of flow accumulation signatures. It's just, I'm really pleased with the way this lined up on this one, and most of it is because of the good work that you guys have done with the GeoWeb face to be able to isolate these production zones. To isolate just Silurian wells is extremely important. Usually it's just a mess is what I get. I get wells of all sorts of horizons that I have to try to decipher and break out. But this, it's done for me, and it's easily downloadable. It's thumbs up to you guys. Now I want to put in our oil fields: Penvis, Covis, Lee, Hamlin, Onondaga, Vevay, Stockbridge, Ingham, and White Oak. We talked a little bit about reef architecture, and the Ryan Garrett and Kaczmarek article. Granted, this is in the Northern Reef Trend is where this is at, but you've got these this reef architecture where they're lined up southwest and northeast, a good rhythm to them, and I'm looking at these signatures in Ingham County, and they match quite nicely with what was going up and up at the Kalkaska 2128 field. Now, I don't know how much scientific worth this is, but I love this next series of slides. One thing ArcGIS allows me to do then is that I can ask it questions. And I said, well, show me, I want to see all oil wells that are within a quarter mile of a flow accumulation signature. So here's my fields, here's my wells, and then let's look at all the wells that were within a quarter mile of a flow accumulation signature. And they line up for the most part, every one of them in one of these existing fields. Like I said, I don't know if there's a lot of scientific worth in this, but it goes to show that there's a lot of these signatures in these fields, and it goes to help prove the point that we do see on the surface indications of subsurface structures. Now I want to break down a little bit on these signatures. So let's just look at these signatures individually. So I wanted to go up to the White Oak field and look at signature 149. 149 we've already seen already. It has oil wells in it. It's got quite a few dry holes in it too, but it's got this beautiful deflected stream flow to the south with radiating stream flow on the northwest, northeast, east, and southeast. I'm going to go down here and signature number 21 down in Penfield. That is radiating stream flow, and 21. You've got a nice linear feature here on this one, and we're finding that these features are not just indicative of differential compaction over a Harf reef chord. They do correlate with faults and fractures subsurface as well. So we may be seeing a fault and fracture along with a reef in 21 right here. But then you go over to 22 and no dry holes, nothing. It's another one to look at right here. Now here's one way out in its own, number 106. It's out in the middle of nowhere. Let's look at this one. Beautiful signature. Good deflected stream flow from the north almost all the way down to the south. You've got a couple of dry holes in the area. Nothing's drilled on this structure. So I think number 6 would be a good one. This is one I'd want to look at with 2D just to see what makes this thing tick. So I got a couple of observations. So the frequency and locations of flow accumulation signatures correlate nicely with the southern reef trend. The first pass of signatures picked up many of the features with oil wells, and the second pass was also fruitful. Oil wells within a quarter mile of flow accumulation signatures correlate with the marked oil fields. And I have a high level of confidence that flow accumulation signatures show a correlation to existing Silurian production. Here, not all Silurian production is associated with a flow accumulation signature. In Illinois, all reefs have a signature, but not all signatures have a reef underneath them, or it's a little bit different up here. A 2D reconnaissance program using flow accumulation signatures will help to delineate existing reefs and be used to discover new reef structures. The use of 3D seismic will be critical to isolate areas capable of oil production. So again, I want to thank everybody at the PTTC, the Michigan Geological Repository for Research and Education, the Michigan Geological Survey at Western Michigan University, and the Michigan Oil and Gas Association. I also want to thank the National Map for providing all the information that we've used here, and Michigan's Geo Web Face too. It's a very nice program. So, data, technology, and practices, new ways to look at them. Thank you very much.